Hello.
Hi, Victoria. How are you?
Great. How are you?
Good, good. Thank you. Hi, Mateen. Am I saying your name right? Mateen Ata? Or how would I say your pronounce your name?
Metin.
Mateen?
That's
Okay.
good.
How are you today?
No, just woke up. It's fine. It's weekend for me.
Oh, that's
How are you?
nice. How is the future? Is it a good day?
Future? we don't know.
Well, you are one day ahead, so you know a little bit more than I do.
Can I send you a link? Can I send you a link about the video, which would be nice to show?
Oh, yes, definitely. Yep, please do.
So maybe we can post it. So maybe it's better to. Sorry, I'm still new to this. How can I post it on the top, or shall I send it to the chat?
I made you moderator, so do you see the leave quietly symbol on the top right?
Yes.
Underneath there are three little dots. If you click
Yes.
on those, there should be pinned link. And
Yes.
if you click on that, you can change the link.
Ah, okay. So it's just one link at a time allowed.
Yeah. Yeah, but we can switch. So perfect. Is the link with audio? Or is it
Yes.
let me check.
It's
Okay. Okay. Yeah. It's working for me, so it should work, I think, for everyone. So that's good. We have a few minutes left, so I'll just share on Twitter that we started the room. And hi everyone. We will start in around 10 minutes. So thanks for coming, and yeah, I hope you will have a few minutes of we have a few minutes of waiting. And if you have questions, please come to the stage or share your thoughts and questions in the room chat. Hi Frank, how are you?
Hello, Carolina. Hello,
Hi.
Victoria, Nathan.
Nice to see you. Mateen, nice to meet you.
Hi, likewise. Nice to meet you all.
I was curious, are you speaking to us through some noise canceling headphones? It was just a bit unclear.
Oh, I can hear him well. I think you have a lot of background noise, Victoria.
Okay, maybe that's I'm kind of driving. But yeah, Mateen sound, I hear him, but it sounds a little not as clear as you and Frank, so I was just curious. But okay, if you can hear, great. Because I can hear everyone else great.
Frank, do you hear everyone fine? I don't know, it could be on my side that it's okay, but for other people it's not. Do you hear everyone fine? Hi Serena, how are you?
Hello,
Hey,
how is everyone?
Good, good. Excited about this topic.
I can hear you all very well.
Yeah, me too. I can hear you well, so yeah, it should be fine. Sorry, Victoria. It might be because you're driving, maybe.
Yeah, it could be. I hear everyone really great except Mateen, but it's okay. If you all hear him great, then that's fine. It just seems to his voice seems to go in and out a bit, like as if there are some headphones, some suspicious headphones. But that's all cool. It's good. I'm happy.
Yep. Mateen meet Serena and Frank. They are also here moderating, like one of our, they're our team, part of the team. So
Hello, Mateen.
Hey, hello.
Glad to meet you. I'm sneaking a
Nice to
peek
meet you.
of the video.
Oh, please, please. So actually, we wanted to have a narrated version of this already out. One of our administration staff from the university, who is a native New Zealandian speaker, volunteered to narrate the story. But we couldn't get it on the website on time, and on the weekend they don't work, so I'm sorry, I have to narrate it for you guys. Please be content with my voice. Sorry.
It'll be fine.
It will be perfect.
Just a preparation question. Metin. What is ancestry? I mean, how old is what time frame in reference to the age of universe?
So we think that the age of the universe from observations is about 14 billion years, and we studied the evolution of those galaxies for 11 billion years.
I see.
So when the
That's old.
It's mesmerizing. I can't wait to hear about it. Are you going to get into some of the details on the size of the simulation? I've got an HPC background, so I'd kind of be curious about how much computation went into this. And
Oh sure, yeah, I can talk about the computational costs and the setup, of course.
great.
Good evening, Dr. Is that Dr. Ata? Am I pronouncing that correctly?
Yes, but Metin is fine.
Mitten, okay. Pleasure to meet you, Doctor. And hiya, Serena, how are you tonight?
Great. Looks like we're in for some really great theater.
I am looking forward to it. I was reading these,
Hi,
yeah.
Jimmy.
I'm even curious about the questions I just came in on and heard Serena asking you already.
I love when you say you're looking forward to a room that discusses the future, Jamie.
Yes, that's true. That's true. It's quite an optimistic viewpoint. Mm.
I remember once when I was at IBM, I was visiting UPenn and speaking to some astrophysicists about simulation. And my background's molecular dynamics, and um, I was listening to them talk about the simulation, and at one point I asked, "Well, what's the conserved quantity?" And they all kind of looked and laughed a bit, and they said every time we talk to somebody that does molecular dynamics, like we get about 30 minutes into the conversation, and they ask, "What is the conserved quantity?" Invariably. So I may ask you that too.
Please, yes. That's a good question.
It's so hard to not ask you questions before the actual events began yet, but have you had a good day so far, Doctor? Metin.
Yes, it's a pretty nice morning. I have my coffee here next to me, and looking forward to the to the conversation we will have.
You know, that's actually our favourite way of hearing our speakers when they're just relaxed with a cuppa in their hands and
Yeah,
just ready to just talk about their passion. Actually, that's one of our favourite things.
yeah. Sorry, I have zero background in this Clubhouse, in the Clubhouse app, and I really don't know how these talks work. So I was just wondering. So they are different. They are like different stages. Some people can speak. Some people can just listen, and some people can raise hands. Or what is the
Well, yeah. So on the
outline?
stage, that are of us that are on stage, we can unmute our mic and talk to you directly. The people in the audience can hear, and if they want to come on stage, they can raise their hand, and one of the moderators can bring them up, and they can ask questions as well. So often we'll have the speaker go through their material. Well, we have some intro, but we go through the material. Occasionally, some speakers are more comfortable with questions, but if there's content and sometimes it's good to get through the presentation, and there'll be a Q&A section, and we'll each ask questions as we think of them, and we bring people up on the audience who like, and sometimes the Q&A gets pretty lively, and so.
Mm-hmm. Oh, cool. Thanks.
But the entire time, our main concern is to make sure that yourself, being the speaker, is enjoying yourself the most and has a chance to talk about your work. So, we try and handle that as best as we can, and bring up some questions that we all would find interesting and engaging.
Okay, and how do I see who's speaking at the moment?
There'll be a gray, so if you look around me, there's a gray.
Great.
Yeah.
Yes, I see it.
Yeah.
Great.
Okay. So it's 9 o'clock, Katerina. Shall we get started? Are you there, Katerina?
Yes,
Sometimes.
I couldn't unmute. I was sharing the room in Clubhouse and it didn't work for whatever reason. Okay, doesn't matter. Yeah, let's start. I'll do it later. Sorry, there is it's kind of annoying. You cannot unmute while you're doing things on the screen if you're on the phone. But anyways, yeah, welcome everyone to the Science Society. We are very honored to have here today Dr. Sedat Ata to give a talk about his really amazing, fascinating research here today. And before we start, let me give you a little bit of information. Dr. Ata's research is focusing on the analysis and modeling of cosmological large-scale structures, and he also observational data and analytical descriptions. And he works in the field of theoretical physics, astroparticle physics, cosmology, and neutrino physics, and observational cosmology. And he did his PhD at Aachen Technische Hochschule and Potsdam at the AIP. And he then moved on for his postdoc, where he is also working right now at the Tokyo University IPMU. And yeah, he wants to understand with this research the structures formed and the universe, and he uses also machine learning and to utilize them as much as possible to simulate different dynamics in the universe. And thank you so much for being here. and for sharing your time and knowledge with us. And before we go to your talk, Victoria usually asks two like general questions about you as a scientist, if that's okay with you, Martin, and then we go into your talk. Thank you.
Yes, absolutely. Thank you very much for the nice introduction. You can ask me, well, anything you want today, scientifically, personal, whatever you like.
Yay, thank you so much. Well, Science Society is so happy to welcome you, Dr. Ati, and please forgive me for the background road noise. So I asked the question to carry us into the body of your research to give a personal side to the talk that you're about to give. And so my question is, if you can think back in your life to a time when you recognized that you felt an affinity for science, that you were particularly struck by scientific thought, and that could be any time in your childhood or your babyhood, or a relative, an experience or classroom, but anything that really felt like you felt that you noticed that affinity. Thank you.
Actually, I have a story about that, if you want to hear about it.
Yes, please.
I think I was about 6 years old, and I grew up in Germany, so we play football. In the US, you call it soccer, right? So I was kicking a ball on my own against the wall, and then got the ball back and kicked it again and practiced my shot. And the wall was consisting of many little bricks, like a brick wall, right? Those red small bricks that are outside of the facade of a building. And I was asking myself, looking at the wall, if there was just one brick, not many bricks, and it went infinitely fast along the wall, would one brick be enough to be the whole wall? So what is the difference between the whole wall and only one brick, which is very fast? And this was it's a child's mind, right? So I couldn't comprehend with the difference and how fast it had to be. And then at some point in the TV, I saw this Einstein's theory of relativity, that energy and momentum, speed and energy is more or less the same, and you can mimic like a lot of mass if it's fast enough, and that really fascinated me. So just by kicking the ball at the wall, I got interested in physics. I think that's like the story why I wanted to be a scientist.
That's so amazing and so unique. And so I ask the guests who come here, and often there's a story that relates to childhood, and it relates to play and experimentation, and the freedom to experiment is, it's just so powerful. And here's this beautiful example, and nobody was telling you to run an experiment, on kicking the ball, or where, or even how you should think about it, how you should process and respond to what you saw. And so thank you so much for sharing that story. And from that time, can you give us a brief, maybe a walkthrough of your path that brought you to the research that you're currently here presenting?
Ah, yes, sure. So after finishing high school, I decided to study physics in Aachen, as Katharina already mentioned. And when I did that, in Aachen itself, I studied particle physics. So you may have heard about the big particle accelerator, which is in Geneva in Switzerland, which collides protons, atomic particles, subatomic particles, and then measures the outcome. So we can learn about the physics of what is matter consisting of. And I found that very interesting, and I got in touch with theories that try to unify quantum mechanics and gravity. So we could also test like microscopic uh, subatomic gravitational interactions with these big experiments. But then the more I studied those theories, the more I understood that I want to move on and study gravity itself. on the larger scale. So I decided after finishing my studies in Aachen that I want to pursue more with cosmology. So because Aachen at that time didn't have any cosmological researchers, not every university can research in all fields. So sometimes you change the university because you want to pursue another path. And I got the offer from Potsdam, which was an astrophysical institute with a strong affinity for cosmology. And they asked me if I would like to do these kind of large-scale simulations, which I do still. So my profile got like sharpened just by moving around, trying different things, and seeing what I like better. And finally, when I ended up in Tokyo, I had the opportunity to also observe with we call observational cosmologists, who really observe the sky and count the galaxies. And then we had like big synergies with my more theoretical affinities, trying to model the distance structures and their expertise in observational data analysis. We concluded to the latest project that we want to talk about today. I think that's it.
Thank you very much. That's beautiful. And at this point, as the other moderators were explaining, you're welcome to deliver your talk and have your Q&A either at the end or intermittently as you like. And so the mic is yours. Thank you.
Oh, thank you very much. So you're welcome to ask questions anytime. Please don't wait for the Q&A. So I will just talk about the latest project, or what exactly am I supposed to talk about now?
Katarina?
Yeah, so I had previously the paper up, but I think you wanted to show this video first, right? And then we can.
Okay. So
But you're free to talk, about whatever you would like to share with us. We don't have to stick to any protocol. It's really
I see.
your
Okay, then maybe let me introduce more like very principal astrophysical things before we move on to the video.
Okay.
Or to the paper itself. So what we talk, one of the things that people have to keep in mind is that if we observe the distant universe, because of the finite speed of light, the more we look into the distant structures, the more we look also in the past, because light needs some time to come to here. For the moon, if we look at the moon, light needs about a second. So whenever we see the moon, it's a second old picture. The same goes for more distant structures. So if we look at the sun is away from us. The distance of the sun makes light take, I think, 8 minutes. So if the sun would go down or would stop radiating, we would need 8 minutes to see it. So already in the solar system, you can see that the speed of light has an impact on our observational abilities, right? And this is still like in the solar system, everything's very close, but we can look at structures within the Milky Way or even outside the Milky Way. We can observe different galaxies. And these observations we use for this work are 11 billion years. So the light travel time of those structures we modeled in this work was 11 billion years. So the picture of the structures, those distant galaxies that we wanted to understand, took 11 billion years to reach us. And now we have to define what is future, what is past. So for us, the present, like now, is of past light cone are those structures 11 billion years ago, because we have no opportunity to observe those structures how they are now, right? For us now is the structures are 11 billion years old. And this is called a light cone in cosmology. So our horizon, we call it horizon. We don't know what's going on there now because the picture we have and the information we can get from those structures is always the picture of the past because of the finite speed of light. And this is exactly what we try to understand in this work, how those structures that we see 11 billion years ago could look now if we forward modeled them. Is this so far clear? Do you have any
Yeah,
questions?
for me it's clear, but anyone else has questions?
Okay,
I
seems to
actually did
be
have a quick
everybody
question,
is
if that's
very...
okay.
Yes,
Just
please.
uh, my curiosity actually was when you were talking about something like, you know, how the light of the sun being, sorry, the moon being a second away from
Yes.
us, right? I was just imagining there, if we were able to look at a planet, and let's say, and it took let's say we saw 100 years, it took 100 years for the light to get to us. So we're seeing 100 years ago, or no, stick to the moon, sorry. Let's say if we saw two people like running a race, and we were always like sort of 1 second or 5 seconds behind or something like that. If we
Yeah.
could zoom towards them at light speed, but we could keep observing them the whole time, would it look like they were speeding up because we were basically matching up our old footage of them to slowly to sync up with what they're currently doing? Would it look like that?
Yeah, that's an interesting question. So when you speed up towards them, the light still reaches you with the speed of light. So it's not only light that is has a finite speed, it's also the information gain. In special relativity, the information content itself travels with the speed of light, not only the light particles itself. So yeah, while you're observing some people in a distance and then you drive towards them and keep observing them, you do see the time changing or apparently changing. Yeah.
That'd be that's fascinating. Thank you very much.
Okay. So this is the premises of the work, right? We observe galaxies that are far away, and because of that, we see a baby picture of those. And in an expanding universe, so we have proof now with experiments that the universe is accelerating. So the expansion of the universe is accelerating, which means the average distance between two galaxies is becoming larger and larger. You may have heard that the universe is like really expanding, right? And that means that the universe's volume at the stage we are observing those structures has been a completely different, a smaller one than now. So the dynamics in that epoch of time that we observe distant galaxies is completely different. And so in order to understand how these structures form, we have usually used cosmological simulations. These are very well established since many, many decades. What they do is they just place particles, like gravitational particles that are mimicking structures. They place it in some volume and then turn on gravity. And then gravitational interaction with time will tell you how those structures like attract each other. But we have also have to keep in mind that the universe, while the gravity is acting on those matter particles, is expanding. So we solve the gravitational evolution in an expanding universe. And then we see how those structures are forming. But those simulations that have been done for many decades now, the what we call initial conditions, so initial set of particles on a grid is just completely random. It's not meant to reproduce any observational structure. We just want to learn how gravity works in those simulations and how structures are forming. And then we can have some statistical analysis, how many structures we see in how much volume, whatever. So they are very good tools to understand the basic question of gravitational interaction, but they are not capable of answering the question of how really observed structures, like we did here, are evolving with time, right? Because they are completely random. So for this work, what we did was the following. We said, okay, we have the galaxies on a three-dimensional volume, so we know how the universe has to look at the right place at the right time. So what we did was we worked hard on an algorithm to get us the right initial conditions to reproduce those structures at the distant universe. So we switch on the simulation at very early times. It's like close to the beginning of the universe, 11 billion years ago. 14 billion years ago, the age of the universe. And then we know, oh, okay, after 3 billion years, when we reach 11 billion years, the structures should look like what we observe. And everything beyond that is the future prediction. And this is exactly what we did for this work. So we found initial conditions that reproduce the data, and then we just kept time moving forward until we reached today, and then we could say, okay, this is the future fate of those distant galaxies. This is the cosmic time machine that we did.
A
And this is,
question.
yes, please.
Yeah. So okay. So I get this. Or I'm thinking I'm getting this. Did you actually have? So you searched for initial conditions, or did you actually have a driving function to drive anything in the simulation toward what we observe? Or that's kind of curious.
So once we start the simulation, we have no handle to manipulate
Okay.
anything
Okay.
anymore. Because so we think that gravity is a deterministic force, which means, let me explain. If I have the same initial setup and I switch on gravity, I will always get the same answer. So this means while gravity is acting, we think it's deterministic, it's predefined everything. We know the exact outcome if we have perfect knowledge of the initial conditions. Actually, this is also, if I may derive a bit, this is also a philosophical question. There was this Laplace demon. It was in philosophical science, a discussion like 100 years ago. If I had perfect knowledge of the initial conditions, if I had perfect knowledge about the driving forces, and I had infinite computational power, I would be able to. So there would be no free will. Everything would be deterministic. That was actually what already philosophers made up their minds like 100 and 200 years ago. Determination against free will was the discussion back then. And it's a very important question. If we consider gravity to be a deterministic force and we say we could have perfect knowledge about the initial conditions, we could always predict the future, at least on cosmological scales. Of course, with quantum mechanics and stochasticity, this all breaks down. But for gravity, in this case, we say perfect knowledge about the initial conditions, infinite computational power, because I want to move the structure forward, always gives me a determined future fate. So because we have some uncertainties in the distribution of galaxies, so the data is of course not perfect. So the initial conditions that we find is only statistically matching the distribution. So within our uncertainty of the data, we say, okay, we find a certain initial conditions, it can explain the data. And then we move it forward. And because we have some uncertainty in the data, the initial conditions can slightly be different, but still reproduce the same structures. And then we get slightly different answers in the future fate. And this is what we did in this work. We found 50 initial conditions that are all compatible with the observed structures. But when we modeled them to today, we got like slightly different answers and did a statistical average over all of them. In this manner, we could say, okay, we have this time machine, but because there are some uncertainties, the time machine has also a statistical uncertainty. So maybe it's a good time now to switch to the video. What do the organizers think?
Okay. Yeah. So I think the audience, if you want to look at the video, I took a sneak peek. It's stunning. It's linked at the top of the room. And so, Metin, why don't you take us through this for those who are viewing the video, you can begin narration.
Oh yes, please. So in the beginning of the video, you can see the sky coordinates. So because we do observations right on the sphere, because we look up in the sky, we have sky coordinates. These are two angles, right? Ascension and declination. And you can see that each point is a galaxy. And yeah, you don't need to consider the colors too much. These are just different surveys that took the galaxies. So what comes now is we don't only have the angular information, how the galaxies are positioned on the sky, we also have, which is called redshift, which we translate into a distant measure. So having two coordinates on the sky and a distant measure, we can make a three-dimensional map of those galaxies. And as you can see, now the galaxies have some structure already. And when we switch now to the simulation, you can see that our simulation at the exact right time of the galaxies matches the structure of the galaxies pretty well. And then we zoom into two structures and move on and switch on the time. And then you can see how those structures will evolve with time. Yeah, and the reason why we think this was a very necessary work is, so usually people observing distant structures, they stop there because they didn't have the right tools to see what will happen to those structures. And then they just measured like how many galaxies in what volume, the galaxy density and whatever, but they could never answer the question, what will happen to those observed galaxies in the future. They think our work for the first time shed some light into this topic. And it's very important to understand it because, let me explain. So when we compare our theory to data, one important aspect is how galaxies are clustered. So, which means in a proximity of one galaxy, what is the likelihood of finding more galaxies? How is this structure formation evolving? And also, we do this for different epochs in the universe. We can do it like for the nearby universe. Then we see a lot of structures that are building bound structures, cosmic web, we call it. But we can also do it for the distant universe, where the universe was more homogeneous. You can see this in simulations, right? The more we go to the past, the more homogeneous the universe looks. So the cosmic web did not evolve yet. And we want to understand how this evolution of the cosmic web takes place and what we can learn from it about the initial conditions of the universe. And therefore, this work was like very well suited to study it with real structures.
I have a question.
Yes, please.
I actually have two questions. So the first question would be on the nature of gravity. And I've always been curious about what a black hole is. And I wonder if there would be any type of connection between a black hole, or would it be possible for a black hole to just be a photon sink, like how photons have gravity, but they don't have mass. So if they were to just be able to suck into one specific location, would that be, at a huge amount of photons in one area? Could that equal a black hole? Question number one. Number two is the supercluster that we are in, Liniakea. Did it come from one explosion, or is it a gathering of space substance? And is there a similar, like a method that why does it look like it looks? It looks as though somehow they were all come from the same like explosion or collision. If you look at the Liniakea supercluster. Okay, that's my question.
Okay, thank you. So black holes in a cosmological context are important. So supermassive black holes, we more or less are sure now that in each galaxy center is consisting of a supermassive black hole, which keeps the whole structure together. So in a cosmological context, black holes are important as a driving force of this in the center of the galaxy. About the second point, that it shouldn't have mass. So we know black holes have mass from gravitational interaction. If you see a black hole, maybe a stellar black hole, which is building like a binary system where some other structure is circulating around the black hole, you can measure the mass of the black hole very well. It also for the center of the galaxy. So just by looking at its gravitational attraction to other structures, we can measure the mass. Secondly, the second question about the Laniakea supercluster. So yeah, that's a very good example for what kind of structures can form in the local universe. You see that structures don't tend to be just a point mass. So there is some driving. So cosmology seems to work a bit differently. Structures don't collapse into one point, but they form like filaments and sheets and clusters and whatnot and large void regions. So Laniakea is a very nice example for the necessity to study how structure formation works in cosmology. And the real origin of Laniakea, I think we try now to reproduce Laniakea with simulations, similar like what I did for the distant universe. But I don't think it all comes from the same point in the space. It forms like more like a diffuse gathering of mass, which then collapses into this giant filament. Yeah, Laniakea is the biggest constituent structure we know of right now, but we are looking hard to find similar structures.
Interesting. Thank you so very much.
So I'm curious about some of the details of the simulation.
Yes.
Yeah, I mentioned earlier, I may get into this. If it's a good time, maybe we could hear more about some of the details of how much computation went into this, and what sort of length scale is the box of simulation that you're
Mm-hmm.
in, and some of those details.
So actually, before we started the simulation, we had to get the initial conditions first. And the initial conditions, so from which we want to start the simulation, took already a few months to computationally get them. So this work consisted of different steps. The first step was to get the data. The second step was to get the initial conditions. Third step was to run the simulation forward again, and then finally the last step was to analyze the final products. And the initial conditions took a few months because the data was a bit complicated. You can see in the video that we had to deal with different surveys and we had to combine all of those. That took, I think, how many? I think, yeah, I used the local supercomputer in Tokyo for that, and the initial conditions took a few months. But after having them, we used a very efficient cosmological simulation code to forward everything. And we did this in a 500 megaparsec cube box with 1024 cube particles. And this took, I think each simulation took about a month to run until redshift 0, which is today. So in total, I think I burned 1 year of computational time on a supercomputer. Yeah, I don't know how much carbon
Wow.
dioxide I produced. I'm sorry.
No,
Yeah, my
that's really
footprint is very
impressive.
bad. So
No,
you know
that's
that
very impressive.
for average people, non-scientific scientist people, like flying is the worst thing you can do, right? But for scientists, it's running on a supercomputer. It's very environmental hostile. So I think I produced a lot of CO2 for this work. like
It does sound a lot more
flying on.
impressive, though, to talk about a supercomputer rather than a flight, though. I have to admit.
Yeah, yeah, it's our biggest the biggest thing we do to the so it's the biggest threat we do to the nature as a scientist to run simulations.
Well, it is fascinating the structures that that you show in the video, how web-like, the patterns of matter are, and if you sort of imagine different length scales, you could be looking at a fungal network or a root system or an astrocyte network, or there's just so many different webs in nature seem to take on this structure. So it's fascinating we see that in the this universal simulation. Did you say you talked in the beginning about expanding universe? Um,
Yes.
is that included in the model here, or?
Oh yes. So you solve the gravitational equation for the test particles you do to which mimic the universe. So we a cosmological simulation works like you place particles, massive gravitational particles in a volume, and then you make them interact. This is one part, but also the background. We call it background equation. We know that we live in an expanding universe. So while particles attract each other, massive particles attract each other, the universe itself is expanding. So these are two competing forces, which make exactly make the universe look like this cosmic webs like structure that we see. If we if we hadn't an expanding universe and we just had gravity, it would all fall into one. At some point, we would just get one big clump of particles, right? Everything would just attract each other and would fall into one black hole. But this is not the case because of the expanding universe. This is always competing, working against gravity. So the final product we get is not like a big clump of mass somewhere in the universe, but this web-like structures, filaments, voids. Yeah, this is a very big achievement of cosmological science to reproduce in simulations exact the same style of cosmic web that we observe in the distribution for galaxies, for example.
Yeah, it's so fascinating. So in it does that is that the dark energy in the model, or is
Yes,
it?
exactly.
Mhm.
We don't know what dark energy itself is. We just know that there's some kind of energy density in the universe that causes the universe to accelerate that expansion. Not only expansion itself, but the expansion gets faster and faster with time.
And so also in the model you would have dark energy for the additional
Yes,
mass that we're not seeing. So you've balanced the dark energy with the dark matter plus the observed matter, in essence.
exactly, exactly.
Wow.
May I
Uh,
also say that I very much love the image you've given of the cosmic web? I actually really like
Mm.
that. Yeah.
Yeah, thank you. Yeah, that's so this structure that you see there is this giant filamentary structure that we found in the simulations. So previous studies always saw like a agglomeration of galaxies, and they argued, okay, this will all collapse into one point, but they didn't give any theoretical confirmation. And we challenged this. We said maybe it doesn't become just one big big cluster of galaxies. And our simulations exactly confirmed us. It will more collapse into like a filamentary structure.
Metin, can I ask a clarification question to understand? I mean, by the way, the video that you share is just amazing to look
Thank
at.
you.
So
Yes, please.
can I get the coordinates, the background of the maybe you call cosmos field?
Yes,
What is the d is so the vertical is DEC is some sort of degree of observation, and then the x-axis is you have r dot a dot. What are these? I understand the length when you rotate become the rectangle. That's the distance, right? That's the redshift. So what are these
Exactly.
X and Y? Yeah.
Okay. So the first, you're referring to the first image, like the footprint of the galaxies,
Right.
right? So we start with two angular coordinates, which are just like angles on the sky. So one angle goes up and the other angle goes like perpendicular, right? It's like spherical coordinates, how you describe points on a sphere.
Okay. So this is
It's spherical coordinates, exactly. Two angles.
sure. So how large is the? Can you give an analogy? Say a moon would give us some sort of expansion. How?
So the diameter of the moon is about 1 square degree, and this is also comparable to the footprint of the cosmos field. It's about the same footprint as the moon.
So it's about 1. Okay, I see.
Yes,
So
1 square. It's about 1 square degree, exactly.
cool. So then, when you say initial conditions, that means you have some, artificial particles and position them among this field that you want to observe, and then you get the data from already available observatory data that fits exactly the 11 the distance, right? Is that
So what we do is those two positions on the sky combined with the redshift information for the distance gives us like a three-dimensional view on how the galaxies were distributed 11 billion years ago. Yeah, and then we try to find computationally, we have some statistical algorithm. We try to find initial conditions, which means we set particles on a grid in a volume. And then if we switch on light, we want to really reproduce exactly the distribution as we see from the data to up to some uncertainty that we have. But let's leave out the uncertainty. So we have the initial conditions at very, very early times when the universe was born. And then if we switch on gravity, we want to reproduce exactly the distribution of those galaxies 11 billion years ago. And once we are fine, we say, okay, this matches them very well. Then we can just keep the time moving forward, let gravity act how it's acting, and then we assume the future fate of those. So yeah.
wait? So that's a two-step scheme to me. So then, which are taken as the initial condition is actually computed somehow according to your model. So when you throw in the particles, are they already coordinated according to the observation data, or is some?
Yes. So in the first step, we start with very completely random distribution of initial particles, but then we have some algorithm to manipulate the positions of those until we assume the right distribution, which we want to see.
I see. So then the first part, what model? So in the two stages, that the equations are different.
The evolution of the universe is exactly the same, but because the distribution of the particles is different, we assume different structures. But the theoretical model and the parameters for, like as we already mentioned, dark matter, dark energy, they are the same. They must stay the same until we reach the distribution that we want.
I see. So then this is somehow amazing that the symmetry breaking that gives you exactly. So that basically the assumption that a random distribution at the very beginning is correct in a way.
Yeah, so it must, because we don't know yet how to place those particles, we start with a random distribution, and then we have some methods how we can manipulate the positions each time, so we get infinitely close to the answer we want. A numerical optimization scheme.
Thank you.
May I ask, please, when you did the simulation, do you know what programming language it was used to actually construct the simulation program?
Yeah, so I myself So we use different use different programming languages. Numerical simulations themselves actually are mostly done in C++, and also modern codes also use CPU, so the central processing unit, and also graphics unit acceleration. So we used GPU programming and CPU programming to do these simulations.
Fascinating. Thank you very much.
Were these were codes written in-house, or did you leverage some other packages?
So these codes were mainly written in C++, but also the final analysis, we like to use Python because it's more handy for data analysis.
Oh yeah. No, I mean, was this code that your group wrote, or did you use a?
The simulation code is called pkdgraph. It's a public simulation code which we changed a little bit.
I see.
But in general, most codes in the community are public. Scientists always publish their codes because other groups can access them.
I'm still a little perplexed by the you start from a random initial distribution and run the equation, and then you get without further
Uh,
input. How do you
sorry,
get?
sorry. No, sorry, the misunderstanding. I'm sorry. Let me explain again. So the first step is to get the initial conditions, right? We didn't start any simulation yet. We just want to have the initial conditions. And to get those, we have a numerical optimization scheme. We start with random, and then we shuffle the particles until we get the right distribution. But we didn't start any simulation yet. Of course, when we start the simulations, we want to start them from the initial conditions that reproduce the data. But in order to get the initial conditions right, there is some numerical optimization that's going on. And within this optimization, the very first step is placing random particles. But then, before starting any simulation, we shuffle those particles until we get the right initial conditions. But this is completely independent of the simulations themselves. This is just to assume the initial conditions.
So then, I guess my misunderstanding comes in the when you from the random distribution distributed points to the initial conditions of yours. In this stage, you're not using the equations. You're using some optimization scheme, and
Yes.
that must have some sort of inputs from empirical data to devise to guide the optimization
Yes.
towards the. Is that okay? So how do you?
Yes, that's true.
I see. Okay. So this part isn't physics, though.
Oh, it is. So you know that the initial conditions have to obey some observational constraint. For example, we know that the universe in the very beginning was very homogeneous and that the meta distribution was according to a so-called Gaussian distribution. So we know that the initial conditions have to obey some physical laws. They must have the right density, they must be distributed in a certain way. So we know that there are some theoretical background what initial conditions look like. And that is used to get those initial conditions of the observations. So the initial conditions themselves, even though the particles can be placed we have some freedom in placing the particles, but there are also observational constraints what the initial conditions should look like. It's not completely up to us. So we have to obey some physical laws there.
So I guess this what will be the alternative? Can you get from the observatory data that are already available, like very precise? So you're not
Yeah.
using that, though. you're just using a generic initial condition points that satisfy those distribution requirements. Which one are?
So yeah, you're right. The observational information that we have, exactly the distribution of galaxies that we analyzed here, they constrain the initial conditions. So you cannot just go and make them as random as you want. They must be in a certain way that they reproduce the data. So in a way, as you already said, the precise observations constrain the initial conditions. And that we use to forward model.
I see. Yeah, got it. Thank you.
Hi,
Thank
Kemal.
you too.
What was the name of the? Oh,
Kemal joined the stage. Hi, Kemal. Welcome. I see you at Brookhaven National
Yes.
Lab. A friend of mine is there. I don't know if you know him.
Ah,
When
who's
can? When can?
who's that? Okay, probably not, because I actually work remotely very much actually. I work from Connecticut most of the time due to the pandemic. Yeah,
Yeah, welcome. Go ahead.
thank you. I really like the talk. I joined a bit late, but Metin, I have a question to you regarding the initial conditions. So I assume that there should be some uncertainty, right, in fixing the initial conditions. And if so, how these uncertainties really affect the total uncertainties in your observables that you make in the evolution process?
Oh, thank you, Kemal. That's a very nice question. So the observations, of course, come with uncertainties. And finding initial conditions that match the data up to some uncertainty is then not unique. So slightly different initial conditions will all reproduce the data up to the uncertainty that the observers give me. And in this case, what we did was to run simulation for 50 different initial conditions that in 11 billion years distance reproduce the data, but give slightly different answers at the final stage. And then we did statistical averaging over all final stages that are compatible with the data. In this case, we took into account the uncertainties of the data itself. We ran 50 simulations, all reproducing the data, but giving slightly different answers because the data is a bit uncertain.
I see. So if the evolution time increases, probably different initial conditions will give you much different results, I believe. So
yes, that's a very good point. So if I may, the data we are analyzing is at redshift 2.3, which is like very early universe, right? 11. So the universe is about 14 billion years old, and we know that the structures we see there are 11 billion years ago, which means most of the so-called nonlinear interactions. So the universe can be described with linear interactions, so the physics is very easy. But the more we come closer to the present time, the more nonlinear interactions we become, so that our analytical models break down and we have to make numerical analysis. So the closer we are today, the more chaotic the interactions become. So even if all initial conditions match the data very well in the early universe, they can give significantly different answers today, as Kemal already mentioned. Yes, the more we model them forward, the more the impact of uncertainty changes the structures. That's very correct and very important point. Thank you.
Yeah, thanks, Metin.
So, as you peer into the future in this simulation, are there some striking comments you could make about how this will evolve forward?
So, yeah, the concept of future is a bit complicated in this context because I mean, for us, the structures 11 billion years ago is the present, right? Because the finite speed of light, our light cone, the structures is as it is today. So this is the present.
So
But
Okay, go ahead.
yeah, yes.
Yeah, in terms of, I mean, were you able to run it forward a billion or 2 years and see what?
Exactly. So what we did was to run them forward to the future in the context of our light cone. I mean, the structure, because it was 11 billion years ago, it should be somehow different now, right? But we don't know because it's outside of our horizon. So we run them until today. So in terms of today for us, and then we saw actually very nice things forming there. One of them was that we were able to statistically, we were able to prove with simulations that this Hyperion structure, this gigantic filament, will not collapse into one cluster, but will form a filament. And that was the first proof of this gigantic filaments that we also see in the local universe, like the Laniakea supercluster. It was the first time we could predict that some structure we see in the distant universe will collapse into this kind of filament. And I think that was a very nice achievement of our method.
I see. So much of the simulated volume we haven't observed yet. Is another
Yes.
way to say that from our light cone that.
Yeah, exactly. So we are looking forward to the new missions, like the new spectroscopic surveys that really densely and deeply cartograph the universe. And then we can make those kind of predictions with much higher precision because we will have much more data.
I actually was going to ask that when I was looking at your paper when it said you're discovering previously unknown protoclusters, and I was
Yes.
wondering like how you could do that in the simulation if you didn't even know they were there. How could you just spot them in the calculation?
Mm. So, yeah, nice point. Thank you. The thing is, the data is the data, right? So the protoclusters are maybe all. So the data tells you how the distribution of matter should be at that time. And then when you move forward the whole structure, you see consistently that at some points always clusters are forming, so bound gravitational objects, and then some points there's nothing forming, right? So the data tells you where a forming of a cluster is likely and where not. So, but when we look only in the distribution of galaxies, we cannot tell yet because they didn't at that redshift at that times. Though these structures have not been formed yet, they are just like a diffuse. So you can kind of guess because you see at some volume that there should be more galaxies than average, and then you usually think that they will collapse into one cluster, but they didn't do it yet, which means consistently forward modeling them, not only looking at the distribution of galaxies, but consistently forward modeling them in time is the only way you can certainly say, okay, this structure will collapse, this structure will not collapse. And by collapse, I mean like form a bound structure. And what we couldn't do it before because the observers only had the distribution of galaxies as a snapshot in time. And they did already a very good job in identifying those overdense regions. But the final fate, of course, is depending on many variables, how the whole universe will evolve, how the nearby structures will evolve. And this is only accessible in this kind of time machine simulation. So we were able to say, okay, there's some region which has not been dedicated to a lot of observational effort because it doesn't look very exciting. But when you take into account the whole environment and the whole evolution, then it will become actually a very interesting point. And this is how we constrain the protocluster regions with our simulations to more precision than was possible at the moment with other methods.
That's incredibly interesting. Please forgive me if I'm not understanding this properly. But this is sounding a little bit like I'm imagining it like if you were watching like a ballet and there's only so many dancers you can see there, but you see that the dancers you can see are responding to something invisible that you can then presume would be another dancer. Is it anything like that, or am I completely misunderstanding?
No, that's a very beautiful analogy. Exactly. So the structures you see evolve in a certain way because there's also structure around them, which is having influence, gravitational influence on them. That's a very nice analogy. Yes.
Thank you, and thank you
So
for
it's
explaining.
also like have you been playing Minesweeper like on Windows like many years ago?
Oh yeah,
Sometimes you
yeah,
have a sometimes you open a number and it's a three, and so the structures around this three determine
yes.
that it's a three, but you don't know them yet. And then
Mm,
if you open everything, you know, oh, okay, now I understand why it's a three. But if you just open the three, you don't know how the distribution around it is affecting it.
fascinating. Thank you so much.
Yeah, thank you. Nice question. More questions?
Yeah, Eli and Vasudev, you joined the stage. Welcome.
Just mainly listening for now. And good to see y'all.
Yeah, sorry, I joined. Sorry, I joined very late. But do I understand correctly that um, you, these simulations are n-body simulations?
Yes, very good.
Okay,
Which means
I see.
they are, we call them n-body because we place a certain number of n gravitational particles in a volume and then switch on gravity.
I see. And the basic question is, yeah. So could you phrase the basic question? You're trying to predict what happens to structures we can see at a certain redshift. Um,
Yes.
and what is the basic idea of this fast forwarding?
Okay, so the term fast forwarding, it comes because, I mean, time, regardless of what we do, time is already forwarding, right? Time is
Right.
moving forward regardless of what we do. So, in order, if we could just keep observing those structures and then see how they evolve, but this would be very fast, and in our lifetime, we wouldn't see anything. So, fast forwarding now means I create simulations that reproduce those structures, and then I can go forward in time and just fast forward them to see how they will evolve over 11 billion years, which I would not be able to see if I just observed them.
I see. So you're simulating conditioned on the presence of these structures.
Exactly. And then
I
I
see.
switch on.
Oh, okay, okay. Thank you.
So
You know, that makes a lot of sense.
we observe them as they were 11 billion years ago. And if we
Right.
can create simulations that reproduce those structures, we can just go until today or even beyond today. We can do what we want.
Right, right.
This is
And presumably
possible.
doing, sorry, go
Yes.
on. Yeah.
I mean, this is possible because in a cosmological context, we assume that gravity is a deterministic force, which means if the initial conditions are constrained, the answer gravity will give you is always the same. So if you have perfect
Right,
knowledge of the
but
initial
if you pick,
conditions, you always get the same answer.
right, but if you picked initial conditions at random, the likelihood that you'd form some structure that we actually see is probably relatively low. So
Mm,
I guess we just took a general n-body simulation and then, gave all n-bodies some arbitrary velocities distributed uniformly. You're probably not, I mean, you probably see some qualitative features that are similar to what we actually have, but presumably you can't make any statements about specific structures.
yes, very good point. So if we looked into if somebody had nothing to do and would run infinite amount of n-body simulations with random initial conditions, at some point you would see exactly the same structure, right? Just by chance.
Right.
But there's there are smarter ways to get those structures correctly
I see.
by constraining the initial conditions. But in general, yes, at some point, because this is like a more statistical question, if you run infinite amount of n-body simulations, at some point you would see exactly the same structure as we observe here.
Sure. Right.
And Metin, how stable those initial conditions are? If you perturb the system a bit for a given initial condition, how would differ your solutions?
So you don't have like a freedom to perturb the initial conditions as you like. You cannot just take one particle and place them somewhere else. You have to obey some distribution initial conditions should fulfill, for example, the meta distribution, the clustering, so that you don't have like completely freedom how an initial conditions should look like. But of course, the uncertainty in the data gives you some freedom in the initial conditions, how they reproduce the data, right? So as for, you can see in the final masses that we claim for the structures we find, with our current knowledge of the data, we can constrain the masses to sometimes up to only 50%, so 50% uncertainty. This is not precision cosmology at all, but in terms of previous methods and in terms of just having a concept to forward model those structures, this is still more precise than anything that has been done until now. The more data we have, the more precise the initial conditions get, and then the less excuse me, the less uncertainty I have in the final masses and the final positions. But with the current data that we have right now, we have about 50% uncertainty in the final masses.
I think this is the point that I was referring to the earlier. So could you just repeat what the sorry, I missed some. I think this is key point. So you're actually utilizing the available data to constrain your initial conditions. So
Yes.
how's that done? Like I missed that part. And so so because of this is a very novel approach comparing to, so that's why your research, right? So amazing, yeah.
How the data is constraining the initial conditions, you mean?
Yeah.
So what you do is the constraint of the data is at a certain time of the universe, at a certain, we call snapshot. So if you stop time 11 million years ago, you know exactly how the universe at that point in space at that time looked like. This is your constraint. You have then the number of galaxies at a certain space-time point. We call it the space-time point. And then you go back to the beginning of the universe, 14 billion years ago, and you place particles on a grid. And then you switch on gravity, and you know that after a certain time, from 11 billion years to from 14 billion years to 11 billion years, when 3 billion years passed, your particles should be structures in conditions.
I'm curious, in looking for good initial conditions to arrive at the the observed data, did you do explorations with running it backwards at certain periods of time to sort of get some kind of informed bias to put in, or at least
Okay.
selection criteria?
So running the whole system backwards to get the initial conditions?
Or at least help in the selection process.
Yes. Yeah, we do some kind of approximate scheme for that. So the problem is there's something called phase space information. What it means is the following. If I want to perfectly describe the dynamics of a system, I need the phase space variable for each point mass, which means 3-dimensional positional and 3-dimensional velocity. Okay, I need 6 variables per point. to exactly know how this structure will evolve. The thing now is, observers give me only half of the phase space. I know the position of those galaxies, but at some snapshot in time, I don't know the velocity, which means I may have like an overdense region of galaxies, but I don't know if they are falling towards each other or flying away from each other. This information I don't have. There are some theoretical methods like the continuity equation or higher order whatever equations that I could get the most probable velocity out of the distribution of galaxies, but actually this is like a part of the information which is missing. So running gravity backwards, that therefore is as such not possible because I don't have all the information I need to run gravity backwards. I just have half of the phase space information. That's why the distribution of galaxies will help me to get the initial conditions, but not perfectly because I just don't know where the galaxies at that momentum snapshot of time are flying where.
I see. No, that makes perfect sense. You didn't have the phase space. Um,
Yeah.
Another question, in I sort of alluded to, and before the room was talking, is the conserved quantity. So in the model you introduced dark matter distribution and balanced that with the dark energy. Was there a conserved quantity, or how did you handle the that aspect of it?
So of course, conservation laws are very important in physics, but globally, the cosmology is a bit unique. Globally, in an expanding universe, you cannot, for the whole universe, there is no point in defining, for example, an energy conversation. Because in an expanding universe, you don't know what's outside the universe, I mean. So if the universe is expanding, you cannot formulate an energy conversation for the whole universe. But locally, in a finite volume, you always can formulate that. So in this case, of course, the number of particles is conserved, and also the code to model the evolution of the structures is energy and momentum conserving up to the expanding universe. So these are the conserved quantities that we have to take into account when we forward model.
But even in the construction of the initial phase space,
Yeah.
were you guided by some distribution of the momentum throughout, or I mean, how much energy did you put in, or?
Yeah, actually, the problem is again that the phase space information is not perfectly known. So we had a lot of freedom in the initial conditions because we don't know how the conserved quantities looked like. So for creating the initial conditions, the conserved quantities are not so important. But then forward modeling them in the simulations, you have to take into account the conservation of energy and momentum and particle number.
Okay, so
Then,
go ahead, Frank.
Oh yeah, actually, that is an important point, I think, dark energy here. So because making, you're saying that the phase space distribution, okay, if we get the whole phase space distribution, we can predict the evolution of the universe. But then if we do not really have, I don't know much about cosmology though, but for the dark energy, we do not really have a control or like how much it affects really the evolution of the universe. And I guess it should bring some uncertainty even to the phase space itself, isn't it? Like if the effects of the dark energy is not known, how can we really know the whole phase space distribution in terms of position and momentum?
So actually, the effect of dark energy is not unknown. We know that a dark energy causing the universe to accelerate the expansion. What we don't know is the exact amount of dark energy and the exact shape. So what we think dark energy now is just a scalar field because we don't know the exact type of it yet very well. But for observations, like with the Planck satellite, when we observe the cosmic microwave background, or we observe the clustering of galaxies, we can constrain the energy density of dark energy very well now. But of course, depending on your dark energy model and the amount of dark energy you put into your system, you assume the cosmological parameters, the structures will look a bit different, definitely. So the cosmological parameters, the energy density of the different energy types that are making up the universe is important for the evolution of the structures. But for the most massive structures that we modeled here, this very big galaxy cluster and very big filament, slightly changes in the cosmological parameters were not so important. We checked it. But of course, the more precise you want to analyze structures, the more important the energy content of the cosmological parameters gets. That's definitely true. But it's always a question of what kind of physics do you want to answer? Do you want to precisely measure the energy content of the universe? Then, of course, you have to make up your mind what dark energy should look like. Or in this case, do you just want to constrain the future fate of the most massive clusters in the observed universe? Then it's less important. But it definitely has an impact, of course.
Thanks a lot.
I guess yeah, it's interesting discussions. Can I make an analogy to learning problem that you're sort of a dynamic programming or whatever, you start with some partially available information in your then say you learned some sort of model, and then you're forwarding that model. So I'm a little bit a few things, right? So for just reading the intro abstract of your paper, there's the keyword self-consistent. That that means that you basically, for each iteration, you're upgrading your your solution, from the previous one. And then
Yeah.
why 11, that's just amazing. You can, because another friend mentioned the nonlinearity. That seems to me that if you can project forward just a little bit, I mean, that along the linear line, that's okay. And then now you're telling us, you're showing this amazing video that actually you're recreating the successfully. Yeah, that is, the whole universe. That's so. Which model are you? Are you using the learned model and combined with, and then you mentioned some other models with dark energy, and what are the factors that you throw in this to achieve this?
So self-consistent in the context, in the abstract of the paper means self-consistently in terms of gravity in this case, because you cannot just gravitationally simulate like a point somewhere and then say, okay, it will end up somewhere. Self-consistent simulation means you have to take into account the whole environment. So which means the evolution in one point in space and time is not only determined by its point itself, but also through its environment. If this point is living in an underdense region, it will have a different fate than it will as it lives in an overdense region, right? Because the gravitational dynamics will be different. So to study the evolution of one galaxy cluster, it's just not enough to just observe this point and then make some predictions. You have to observe the whole field, like what we did there, and then model the whole field, because gravity will act regardless. One point at the end of the box will gravitationally interact with a completely point at the completely other side of the box, right? Of the simulated box. Which means only if you take into account all this environmental structure self-consistently, you will get a valid answer of what will happen to singular structures. And your question about learning, yeah, so We do a method which is called Hamiltonian Monte Carlo to get the initial conditions, which samples the probability distribution of what the initial conditions should look like. So it's a Markov chain Monte Carlo scheme, which depends on it's an iterative approach, and each iteration in the next step takes the information of the previous step and updates our information of how the probability distribution of the initial conditions look like, and then at some point we reach after many iterations we reach the so-called stationary distribution, from which we know, okay, up to our statistical model this representation of the initial conditions is legit and it's a valid sample, so we can start the simulation from.
Sorry, so here, what is your ansatz for the steady state distribution, which is like the potential term in the HFC?
It's the distribution of the galaxy density.
I see. And the idea is that you do HMC to basically reach steady state with the distribution that you are sort of conditioning on. Is that right?
Exactly. Yes, it's very
Okay.
right.
So, okay.
We discretize the volume, so we count the number of galaxies per certain voxel in our volume, and this constrains the amount of dark matter we expect there, which then in turn constrains the initial conditions.
Okay, thank you. That makes a lot of sense.
May I ask, when I was reading your paper, I was wondering what exactly is a giant, what's it called here? Giant filamentary supercluster, because that sounds so cool.
Yes, the terminology is a bit of up to our taste. So there, if you look at the amount of structures given some mass threshold, so the more massive the structures get, the less frequent we observe them, right? There cannot be a gigantic supercluster in every corner of the universe. It would just violate all the statistics that our universe has to obey to. So the more massive the structures get, the more unique also they get, right? Because at some point you do expect a lot of matter to form, but at some other point in space you expect a gigantic void, an empty region to form. So we chose 10 to the 15 solar masses as a threshold to be a very massive structure. And this giant Hyperion supercluster, you can see it consists of up to 4. If you see the video or the plot we put in the paper, you can see that more than 4 or 5 individual clusters that are interconnected along a line and along a filament make up this filament supercluster.
Thank you very much. I can't, like, just to mentally conceive of something so enormous is just mind-boggling. Thank you very much.
Yeah, thank you too.
Okay, so I have a fun question. I'm curious about this expansion of the universe and its rate that you found would balance and explain the data. Another fun fact I heard some time ago was from an astrophysicist making a cute comment about the rate of rotation of the Milky Way was such that the last time dinosaurs walked on the Earth, we were on the other side of the galaxy. And I'm wondering, so with a rotational period of 250 million years, given the expansion rate that you found in your model balances things, in that kind of period, or a billion, or some reference period, how much of the universe was, or how much expansion occurred? Maybe in terms of near galaxies getting farther, or from the center of your simulation box to the edge, or is there some reference number that you have
Yes,
on
we
hand?
can actually very precisely calculate it. 11 billion years ago, I think the universe had like 20% or so of the current extent. So the universe was much, much smaller than now. So the dark energy evolution equation in cosmology actually tells you how big the universe was then. So it was just a tiny fraction of the volume that it has now.
Okay, so the extent of the simulation that we have not observed yet, the universe is basically gotten 5 times larger.
Yeah. So that's sometimes a bit confusing. Let me try to explain. So the light so the galaxies emitted light 11 billion years ago, and it arrives to us now, right? 11 billion. So the light traveled for 11 billion years. Imagine there were aliens and they sent us a hello signal, which arrived now, and now we want to send them some signal back. It will not take 11 billion years. It will take much longer because the universe has expanded in between. It will take like 17 billion years. So while we received the information of those structures, the universe underwent an expansion, which means that the horizon for them when they sent the signal is a different one than ours while receiving it.
Right.
That's
No,
really
that's cool.
interesting. Yeah.
Yeah.
I hope when you saw the future, when you saw the galaxies billions of years in the future, you didn't see lots and lots of little McDonald's and stuff all over the place. That would be depressing.
So the concept that we use in cosmology for that is the horizon, which means what is causally connected to us. So any structure that we can receive information from is our horizon, but if we send information to those structures, the horizon of them towards us could be different, because the universe is expanding in between, and also because of the accelerated expansion of the universe, our horizon is meant to shrink. We will lose connection to parts of the universe because we undergo accelerated expansion, which means that some structures, when they send information to us back then, we will never be able to answer them because they are out of our horizon now. Sorry, please say again.
You're in the Matrix, Serena.
Yes, Serena, sorry, we couldn't get what you said. So yeah, the concept of the acceleration and the expansion makes things very difficult in terms of horizon and information gain.
That is incredibly interesting. Do you have any like when you went forward in the future with these simulations, do you have any idea of going beyond what you've already modeled, or does it become too,
Yeah.
does the uncertainty become too much?
In principle, that's a good point. We can, so we modeled those structures until the time which is today for us, for 11 billion years. But of course, you can always go you can keep forward modeling. But what we see is exactly because of the evolution of the dark energy, at some point the cosmic evolution will freeze, which means everything which has collapsed and formed structures stays as it is, but no new structures get formed because the dark energy is just dominating the universe. This is what we think now. If we extrapolate the evolution of the dark energy to infinite times in the future. But of course, it can be different. Maybe there's some dynamics in the dark energy we don't know, and in future the universe will start shrinking again. We don't know yet. Everything we can do if we model everything to the future, is to extrapolate our knowledge from today until infinity. And if we do that, the universe will undergo infinite expansion. but we don't know if it's true.
Can
Right. Oh, sorry.
can I ask? So since everything is expanding and we will lose contact to a different um, other clusters and structures, will that affect how they behave? Because of the quantum, or is the quantum world basically not included in this, like quantum physics, because of this observer effect, and then it basically changes the behavior from photons. Does
Mm,
that affect anything, or no, not really, because they're still, there's still a network there, just not connected to everything? Or will it change the dynamics because it's kind of a network but a cluster by itself and not anymore connected to anything else?
mm. So your question is, if we lose connection because of if structures move out of our horizon, could the physics also change there?
uh,
And
not the laws, but maybe, yeah, I don't know, yeah, maybe.
mhm. So that's an interesting point. I mean, we would need to make experiments in other parts of the universe to see if the quantum mechanics there works the same as here. But what I think, because at some point in space-time we were connected to those clusters, the physics there should be the same as the physics for us and also for quantum mechanics. Just because we lose contact to them because they move out of our horizon doesn't mean that the physical world there should change. It's just that the connection, that's the information we can share is just different. It's just gone.
Okay. Yeah, I come probably from a biology perspective, where
Mm,
you start having, evolution starts moving away from each other when we are physically separated. The Galapagos,
yeah.
you know, that they're
I mean,
evolving in different ways when
I think
it,
yeah, it's a very interesting question. So also in quantum mechanics, we have this information exchange. We have the entanglement and whatnot, right? In quantum mechanics, and how does this change also when parts of the universe are disconnected? Yeah, it's
Well,
a good question. I don't know.
you basically have the information loss paradox in reverse because you have a cosmic horizon where things
Yes,
can
yeah.
only leave. I
So
mean,
also
there's
in
the radiation, right? The Gibbons-Hawking radiation, which also you get
yeah,
just like the
you
Hawking
mean
radiation from a black hole.
yeah, you mean the information paradoxon of a black hole, right?
Exactly. Yeah, you have sort of
Yeah,
the inverse
yeah,
of that.
of course, yeah. I mean, if you can't share information with some parts of the universe anymore, also our gravitational potential here will not affect those structures anymore. So the universe will do change if it moves out of our horizon. But what exactly it means for like quantum mechanics, I'm not sure. Sorry.
I was wondering, do you know at all if the simulations that you've done now, of the universe and expanding and everything you've discovered from it, do you know if this has actually helped to confirm or refute any other current theories on the universe at all?
Um, the data is not precise enough to rule out some models yet. We just did this work in order to like measure the final state of the structures. But the better the constraints get in terms of galactic distribution, galaxy distributions, we would be able to answer also the model dependency of our work, definitely. But at the moment now, with the data we have, we cannot rule out anything.
Ah, okay. Thank you.
Yeah, actually, I'm curious to hear your thoughts, Metin, on using this kind of logic in the context of eternal inflation, where there's
Yeah.
famously a measure problem. And if you try to, you know, find a conditional probability for the existence of, our patch of the universe, then, it comes out to be zero, just because
Mm,
you don't know how to put a measure. Whereas if you were to post select and say, well, okay, some inflation gave rise to this particular patch, and then what could possibly have come before, then maybe that's a way of sort of segmenting that. I'd be
Oh,
curious to
definitely.
hear.
So we cannot constrain inflation models yet precisely with this kind of work, but what we can do, which is also very important, is we can constrain the dynamics of the initial conditions. So there's also something called like primordial non-Gaussianities, which is predicted by some inflation models, which says that the initial conditions should not be completely Gaussian distributed, but some tiny freckles should be non-Gaussian. And by forward modeling real structures and see how they evolve, you can actually you can give answers about the statistics of initial conditions, which then in turn can help to constrain inflation models. This is
Yeah,
definitely possible.
that sounds very promising. Yeah, I mean that's
Exactly.
like famously hard, right? Yeah.
Yeah. So you can
Actually, I
say
have. I mean,
like what kind of, yeah, please.
sorry. No, I mean, I just had a sort of tangential question since we're talking about non-Gaussianities, and this would be, I guess, equivalent to measuring non-Gaussianities in what people call the matter power spectrum,
Exactly.
because you've been inferring this from the galactic surveys.
Actually,
I
the
don't
meta
know.
power spectrum,
Uh-huh.
before we move on to the meta power spectrum, all that stuff, it's just what we call a summary statistics. So we have the distribution, the three-dimensional distribution of galaxies, and we compress it into summary statistics. But with this kind of work, you can do it on the field level. So you have the distribution of matter on the field to extract information, which is much more powerful than the classic summary statistics.
Right. I see. Yeah, actually, I mean, I had a slightly tangential question since we're on this point. There were recently some claims that within the data, some people have observed parity violating 4-point functions.
Yes.
Um, do you know anything about this? I mean, one paper says it's 7 sigma, the other says it's 3.5. I mean, is this a real effect in your eyes, or?
It was like from last week, 2 papers, right?
Yeah, yeah.
And so it's also very new to me. But I mean, so there are two groups measuring it simultaneously, but kind of they worked together in the past. So I don't know how independent those measurements are actually. But also this parity violation is very new to me, and I'm very excited about it. But I never worked on it. Sorry, I cannot give you further information.
It's all good.
Mm.
But thanks.
Curious, a parity violation of what? I missed the keywords.
So they claim to have measured the parity violation in the distribution of galaxies and parity in a gravitational context. So that how structures do behave under certain transformations.
Yeah, roughly speaking, they're looking at statistics of tetrahedral configurations of overdensities of galaxies,
Mm.
and they found that the distribution they observed in sort of one part of the sky didn't really match what you'd get by just flipping, taking the perspective and the mirror, sort of the mirrored part of the sky. Roughly speaking, you look
Yeah,
at
so parity,
tetrahedra,
exactly.
and then you just, yeah, for whatever reason, you look at the mirror reversed version of the statistics of these tetrahedra that you see, and they're not the same.
Who are the
Wait, so
of the paper? Do you know? So,
I know one of them which we used to study together in the SDSS collaboration. So there's one single author paper and one with more authors, and I know the first author of the one with more authors.
can I just throw in a basic educational, like just to make up the background? The CMB that we're getting the data, are they supposed to be like parity according? I mean the new version, like sundry version, it has a
So
symmetry.
so
Is
this
that correct?
the CMB itself is a two-dimensional map. while the distribution of galaxies is a full three-dimensional map. So the symmetry is a bit different.
Right, and these would be like, I mean,
Triangles.
you'd have to take them back in time, so to speak, if you
Mm-hmm.
wanted to sort of trace them back to the CMB, and they would be like these like non-Gaussianities, which are sort of very, very hard to actually try and track down in the CMB. I mean, you can barely see the deviation from utter Gaussianity in the CMB. So
Yeah. So the CMB actually ruled out a lot of inflation models with induced non-Gaussianities. But there's still some room left, which could be realized in nature. We don't know yet.
So that implies some additional, like say, at some point of the time that the asymmetry caused by something. I mean, I'm just
Most
saying.
probably some inflation models previous
yeah,
to what we
multi-field
observe in the CMB. They are multi-field or strong,
axions and so on.
yeah, strong some derivative models. They can predict slightly different statistics in the CMB, which we should be able to observe in the CMB. And also then, if you have it in the CMB, it propagates through gravity. It also propagates to the evolved cosmic web which we observe today. So we should be able to see some deviations.
Isn't your algorithm or structure architect? I mean, what you developed is just fit for this study. Give some tweak on the initial conditions and see the time evolution of
So
asymmetry.
so we are able to constrain the initial conditions with the current data only on megaparsec resolution, which is too big to constrain any effect which is below, and the non-Gaussianity would be below this effect yet. But the better data we get, the more precision we get into the initial conditions. At some point, I'm very confident that we also, with these kind of methods, can constrain primordial non-Gaussianities at some precision at least.
Very interesting. So, can you? I mean, my earlier question regarding what are the components that are in the app? Say, I do see the keywords of proto galaxies, and also one of the contributions is that you identify previously unidentified lower mass ones in your initial conditions. So starting with these initial conditions that you obtain, and you're able to somehow the simulation shows that in some sort of measure that fits what we observed today at z0. The and so there's a dark matter, dark energy model, the gravity. What are the physical components in this frame of this the second stage from the initial condition to today?
Sorry, I'm not sure if I got the question correctly. You asked about the structure of dark energy.
No, I'm just curious, without reading your paper. I'm just trying to get the idea. So, what's in the model of say with the initial condition in hand?
Okay. Okay.
Yeah.
So what you need to make a map fast forward the universe, you need the cosmological parameters of this. Work has been done in the so-called concordance lambda CDM model, which we use at the moment mostly in cosmology, which gives which is based on a few parameters like dark energy content, dark matter energy content, if, strength of fluctuations, and so on. And also it says that it's a bottom-up theory, which means in our current understanding of the universe, we think that small structures form first and by subsequent gravitational attraction form bigger and bigger structures with time. Also, there has been, in the Cold War times, there was not only a military Cold War, there was also a kind of a scientific Cold War, where scientists from the East also claimed that the top-bottom model should be considered, which they said the universe first realizes the biggest structures, and then by fragmentizing those big structures, small-scale structure forms. So the question of first the small or first the biggest structures formed was actually a very vivid discussion in cosmology over the last decades. So we now concluded that, or we think simulations show strong evidence that the bottom-up method is theory is the more reliable one. So we think that small structures form first, and then subsequently merge and merge and merge until the bigger structures pop up. So this is one premises. The cosmological parameters are premises, and also how the clustering of the universe should look like today. We put this assumption into the simulation too. So we cannot, the so-called clustering and abundance of galaxies is very well measured. And this we also use as a constraint to run the simulations.
I see. Yeah, thank you.
Yeah, I think you have been here for a while now, and I wanted to check with you if you if you're still open for a few questions, or if you would like to take the opportunity to get rid of us, basically.
At some point, I would like to eat lunch, but
Yeah,
I think like 15 more minutes. Is that fine?
yeah, sure. Thank you so much. Really
Mm.
appreciate it. And I realized when I was looking up your bio that you grew up in Aachen. I grew up in Bochum. It's not really far, so close.
Actually, I am from Bochum. I
Oh,
went to
you
study
are?
in Aachen.
I went to Ruhr-Universität.
Okay, nice. I never went to university in Bochum.
Ah, okay. Where did
That's
you
so
go to
cool.
in Bochum? Which
Actually, I
school?
went to, no, in school-wise, I went to in Hattingen, which is next to Bochum.
Oh, in Hattingen. Yeah, yeah. Okay.
Amazing, amazing.
Hattingen is way prettier than Bochum. I like
Yeah.
Hattingen.
Oh, thank you.
Yeah,
Long time I've
especially
not
the
been there.
old. Oh, you like Bochum better?
No, I like Hattingen
Yeah, yeah.
better.
Nice. It has this really old town, like small old town for everyone. It's
Yeah,
like really still preserved, kind of. It's really nice. The Weihnachtsmarkt is really pretty there.
yeah,
We used to go there. Okay,
yeah.
sorry.
You're
uh,
welcome when I'm there anytime again, all of you.
oh,
Oh,
you
that is
live there
wonderful.
still? You going back there soon? You're going to?
Unfortunately, it's been a while since I've been there, but I would like, yeah, I still have many friends from school and so on, and they graduated.
Oh, okay. Yeah, my parents still live in Witten, and my brother,
Ah, amazing.
he's a medical, like he's a neurosurgeon in Essen now. He went also to
Mm,
university. So part of my family still lives there. We should meet up
amazing.
one day.
Definitely.
Yeah,
Get the get the Glühwein in the Weihnachtsmarkt.
exactly. Funny.
The
Okay.
Science Society has yet to go on a group field trip, so
Like the Weihnachtsmarkt is really pretty there. It's really nice. Like, the Christmas markets there. And it's not too big. It's not like those humongous ones. So it's nice.
um, I have a quick question I just thought of just now. Was that when you got the results back from your simulation, was there anything that you observed in the simulation that you actually found surprising at all? Like
So,
completely different to your expectations?
mm, Yeah, I found it very surprising that, as mentioned before, some of the protoclusters that have not been identified yet, they were really, really consistently forming at the same spot, even though the data didn't really constrain the structure there, but only the structure around it, the environmental structure. So we got really precisely, consistently in 50 simulations, the same collapsed structures in all realizations, and that was really astonishing. That already, like mildly knowledge of the galaxy overdensity in some region can put this strong constraint into one region. We have not been aware of that before, and I think that was a very nice outcome.
That is interesting. And what can you extrapolate from that? Or at the moment, is it just that's interesting, or can you actually extrapolate something from that?
Yes, we can. We can actually help observers now who look into some region in the sky and don't know what they look for. We can tell them at that distance, at that redshift, at that time of space, if you observe this kind of structure, it's very likely how it will be evolving. And we can tell them with to some precision what kind of environment they can expect around these structures. In that sense, our simulations really help to shed light into the probability of distributions at that redshifts, what observers can predict, can expect to observe.
That's pretty great, right? Because at best, your model will actually help confirm what they're observing and vice versa. And also other at best, it doesn't, in which case you know what to reconfigure for next time. So it's a win-win, isn't it?
Yeah, so I hope that some of the structures that I predict could be dedicated and could be have a dedicated observational campaign being run and either confirm or maybe challenge my assumptions. That would be great.
Will you have the chance to have a cluster named after you?
No. Please no.
One last thought I've got as well is it was in my brain a second ago. Give me one moment, please. I'll come back to me. Yeah, it was. Yeah, that's what it was. So with your simulations, of course, you're going by everything that we currently know, or everything that you could possibly put into the simulation to make it as accurately as possible. But considering the fact that we are always discovering new things about science and physics and everything, how big a discovery would we need to discover in order for you to say, the simulation is now not really tenable? I mean, like if we discovered, I don't know, like a new behavior of gravity or something like that, how big would the discovery have to be to shake up your data in a major way?
Yeah, that's a good point. So what the key question I wanted to answer is how likely these very massive structures are realized. And if we look at different patches in the sky, and we always see that the structures tend to form two big structures. If the abundance of those supermassive filaments, giant filaments, are too high, then it would challenge our current understanding of the universe, because the number of those very massive structures is predicted from the Lambda-CDM theory. There cannot be too many, but it's mostly calibrated on the local universe. We don't know yet very well what goes on in the distant universe. And if we keep finding those very massive structures in the distant universe too often, this would be a very nice challenge of our understanding of the current theory.
I'm sorry, I can't help laughing with the size that you're talking about, and you still call it the local universe.
Yeah, sorry. That's what we
It's
do. Sorry.
it's not, it just mind boggles the kind of size you talk about, with the universe. No matter how big you think it is, it's always bigger. I love that. Thank you so much, Doctor.
Thank you.
So the clusters, so this clustering, it's mostly driven by dark matter, or
It's competing dark matter attraction and dark energy repulsion.
Oh, okay. And because that is that kind of a constant too, and that's why these clusters keep appearing.
Mm-hmm. If
Because
we
that's
hadn't,
constant. Okay.
if we didn't have any dark energy, everything would presumably just fall into one big, would keep accumulating mass until we are ending up in one black hole, because gravity would keep running, would accumulate matter more and more into one point. There is no force which is competing, right? But because we know that the universe is expanding at some rate, and the expansion is changing with time, those structures form. So sometimes we have a collapsed region, and then it stops collapsing because the dark energy is taking over.
So in
Well,
time, so do you see time as an equivalent of entropy, or is it different?
Yeah, so
Your
depending on the cosmological model, of course, entropy is rising when the dark energy is the dominant force, right? So yes, if the state of um, the 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 model for dark energy in the equations we solve in the background equations, if it stays like that, how it is now, it will completely dominate the universe in the future, which means also that we will just freeze out. Everything will be maximally distant from each other, and entropy will be maximized.
okay.
But it does, yeah, we are extrapolating the knowledge we have now to infinite times in the future, right? And there's maybe dark energy behaves differently in future. We don't know yet. Maybe there's a mechanism which we didn't model.
So kind of the contraction and bouncing back of
Yes,
model.
exactly. Maybe, yes, maybe that happens. We don't know. We can just say
So
that we observe the universe is undergoing an accelerated expansion at the moment.
So this is kind of a fun more question. Don't take it too seriously. It's something my young son and I came up with because
Mm.
very afraid of dying and that the sun dies and the universe dies, at some point.
Mm.
And
Yeah,
I came up with the solution because a biologist. I say, oh yeah, we find rejuvenation stuff right now. And he say, okay, but then the earth dies and the sun dies and the universe dies. So we came up with the solution that we could, if we find a parallel universe that goes the opposite way, and we create kind of an AC connection, we could dump our entropy in the parallel universe in case it's make an enclosed system, right? Do you
mm.
think there's any possibility for that?
Mm-hmm.
Yeah. Sorry.
Yeah,
Question.
nice. It's
um,
nice.
I had one other image I would like to wonder if it's accurate. It was interesting when you were describing dark energy a second ago, and you're describing that if it wasn't there, everything would just cluster together to one huge black hole. Yeah.
Yeah.
Um, I was wondering, like in my mind, I'm trying to picture it, and how I'm imagining it. It's like if you spill like our universe is like spilling milk all over the floor, and
Mm-hmm.
as it's pouring outwards, it's still pulling around like the leg of the chair, of a cup. All the other structure, the cup and the table and everything, they're all dark matter. Like they're other, or maybe even just a foundation of the universe itself. Is that like how it, it's kind of being observed? Is that how your guys are picturing it? Like in that sense, like that's why it's not all coming together. That's why it's being split up and pouring all around and things like that. Or is my imagination just completely going crazy?
I didn't really understand. Sorry.
Oh,
So,
okay. So I was imagining like our expanding universe, like kind of milk that's been spilt on the ground, or
okay.
liquid, right?
Okay.
So as it's expanding outwards, right? Because there's other structures like on the ground as well.
Okay, sorry. So, yeah,
It's
yeah, no, I get it.
mhm.
Let me answer. First of all, we are not expanding outwards, right? We don't have any
Oh,
boundaries. We are
oh,
expanding inside ourselves because we don't know what's outside the universe. So this kind of, unfortunately, this kind of imagining doesn't make sense because we don't know where we are expanding into. So you
oh,
you you imagine it like blowing up a balloon and expanding the balloon against the air around it. And we don't know if that
yeah.
is that a good analogy or not.
Oh,
And
So
okay.
that's why also energy conservation in the whole universe doesn't make any sense because we don't know what we are expanding against. So we would need to know what is outside the universe to know what we are expanding into, but we don't know. We don't even know if this makes sense to us.
so could we,
Right.
in case we could generate artificial black hole, a tiny one, and
Yeah.
we would have dark matter or dark energy, like we could harvest or control that too. If you would point it with kind of a dark energy laser gun, could we dissolve a black hole? That-
On like lab grown black holes, dark energy, and dark matter don't have any like very limited impact. Dark energy just
Very
becomes
small black.
it becomes the driving force on galactic on really cosmological scales. But also, I mean, I don't blame dark energy for expanding my body, right?
Right.
I
So
would know.
very small
Yeah,
black holes you would form in the lab would just evaporate away anyway.
Yeah, they are ought to evaporate due to Hawkins radiation. They are not stable. At least we think so at the moment now.
yeah.
But yeah,
It's
it depends on the
all.
scale
Oh, okay.
at which we look at
Okay.
things. So the galaxy, our galaxy also is a bound object, right? So independent of dark matter, it will not rip apart because it's gravitationally bound. But for the space between galaxies, at some point, dark energy will cause them to lose connection.
Okay.
But what is gravitationally bound? It's gravitationally bound.
Okay. So it's not a antidote to a black hole, basically.
No, not.
You know.
It depends on the scale. If you have a cosmological sized black hole, you could do something with it, yeah.
Okay. Oh, only in that scale.
Yeah,
Oh, okay.
depends on the scale. Also, our solar system would get ripped apart, right? If we injected more and more dark energy, but it's gravitationally bound. So always you have to think about the scales at which those forces are dominant.
Oh, I didn't know that. I learned something
Mm.
that it only works at such a big scale. I didn't know.
Mm-hmm.
Or thank you. That's interesting.
Curious, what your comments would be on the modified Newtonian dynamics mount that
Mm-hmm.
Milgram.
Yeah, yeah.
Yeah, I mean,
So
since we're talking
of
about
course,
gravity of a large
yeah.
scale.
So not, of course, not all scientists agree or try to get. So there are still a lot of unanswered questions in Lambda CDM2. Even though it answers many questions, there are some places it fails or it's not precise enough. And of course, not every scientist has to agree with the concordance model. So there are many alternative models that can mimic expansion of the universe, but without any dark energy, without any dark energy content. One of them is like this modified gravity models that say that gravity on different scales acts differently. So even though gravity, like in our solar system, or if we just drop something on the Earth, it works as we know it. But on cosmological scales, it's different from Einstein's equation, the field equations. And those also we run simulations to see how those alternative theories could explain the universe. But also, they even though they are like more elegantly solving the dark energy, the expansion problem, which we think is a thing now, they come up, they create other problems. Like I think Mont cannot very well explain like gravitational lensing, which is very well understood in lambda CDM, or other things. I think so. None of the models we have is really describing the nature is this, right? Because we can't comprehend it. we pack everything into models and try to make predictions. And I think Mond comes with a lot of problems, other problems on non-CDM, so I haven't really worked on it. But of course, in the context of cosmology, we should be open up our minds. Maybe gravity does act differently on cosmological scales other than galactic scales. Yeah.
Thanks.
A question about availability of your data set. It seems
Mm-hmm.
like an amazing amount of computation went in it, and it's a really fantastic result. And I'm wondering if, on the availability, if things like Unreal Engine 5 type metaverse representations of that data could be constructed, but even that would it would be fascinating to fly through the universe as you've derived derived it in this simulation. But it's also interesting to think that each voxel implies a certain within that scale distribution of matter, and it'd be interesting on a further process as a rendering add-on algorithm that would produce some similar distribution consistent with the today representation of each of those voxels, being able to
Yeah,
fly through that.
that's a very nice point. Yeah. So the uncertainty within a voxel or a change of our simulation voxel by voxel also encodes information how well we understand the universe. So the spatial uncertainty of our simulations is actually, I mean, it's not a nuisance. It's not annoying. There's information encoded in the uncertainty of the distribution. That's a very good point. Yeah. So the data is available, of course. So it's a scientific courtesy to make everything public that we produce, so other groups can use it and learn from it. But I think it would take some time to have like really nice visualizations, as you mentioned, as you suggested with it.
Yeah, it's a kind of I'm sort of once again ramping up and yet another Unreal Engine 5 now. It'd be a great project to start with that data set and produce some kind of renderings that would be really fun to fly around in.
Yeah, yeah. Or even in VR modes.
Oh, completely, yeah.
Definitely.
Okay, I think we stretched your time again to 20 minutes
No problem.
15. But yeah, thank you so much for sharing all this knowledge and this model, and also your time with us. You answered so many questions and also my silly nonsense questions, so I really appreciate
No such thing. So I really salute the curiosity of all of you. I really appreciate that you take your time and study something which is not related to your work or whatever. I really I salute your curiosity for new things. Thank you so much.
And thank you so much for giving us the time and opportunity to speak to an expert. It's very, very rare someone like myself, who's just a layman, gets this opportunity. So it's a true privilege. Thank you so much, Nathan.
Thank you all.
Yeah.
And if you have more questions, you can just text me here on Clubhouse. I'm happy to answer more questions if you have any.
Yeah, thank you so much, and feel welcome to come back anytime, or once you have something you want to share
Okay.
again with us, feel free to come back. And yeah, it was a great honor. Thank you so much, and thank you everyone for coming and participating in the discussion and sharing your questions. And yeah, enjoy the rest of your weekends, everyone. And yeah, follow the club if you like discussions like this. The next room will be our weekly recap, where we'll kind of summarize in an hour what we learned throughout the week. And then if you like to go deeper into, you can listen. recording. So thank you again, Martina. Um, Happy weekend, and yeah, enjoy your Saturday.
Thank
Thanks.
you. Take
Bye.
care, everybody.
Thank you.
Thank you.
Thank
Take
you.
care.
Bye.
Bye bye.
Bye.
Bye, everybody.